Hi, folks. I'm just finding the beginning of this lecture. Here it is. Real gases. So, up until this point, we have been discussing ideal gases, and we've been applying the ideal gas law, PV equals nRT, also known as PIV-NERT. But in real life, we have real gases, and let's face it, there's no such thing really as an ideal gas. So, what makes an ideal gas ideal? What are we leaving out when we talk about ideal gases? Well, we're leaving out the fact that real gases undergo intermolecular interactions. That means that they collide with each other. They're attracted to each other or they're repelled by each other. So when we use the ideal gas law, we're leaving out the interactions that really occur between gas particles. The other thing that real gases do is that they take up volume. Okay, real gases actually occupy space themselves. So we can't only consider the volume of the container, right? For real gases, we would have to consider the volume that's occupied by the gas particles themselves. So in order to do that, there's a special equation that takes the ideal gas law and corrects it for the pressure and the volume to take into account intermolecular interactions and the fact that real gases take up space. And that equation is the van der Waals equation. So the van der Waals equation is a corrected version of the ideal gas law. And in it, we take the observed pressure, which is the pressure of the real gas, and we correct it using this A factor. So this A is a pressure correction. I'll talk about it a little bit more in just a minute. And you multiply A by the number of moles divided by the volume of the container squared. So what this term represents is the ideal pressure, the pressure that we would have as an ideal gas. So basically, when we actually take a pressure measurement, that observed pressure is going to have to be corrected if you want to make it match the so-called ideal pressure. The next term takes the volume and then subtracts this factor B. B is a volume correction factor multiplied by the number of gas molecules. And what that does is it corrects the volume so that we can have the ideal volume. So in this term, the V is the actual volume of the container, and the NB is kind of subtracting the volume taken up by the gas particles themselves. And if we subtract that, then we get the so-called ideal volume. So if we take the corrected pressure and multiply it by the corrected volume, we get nRT. So this van der Waals equation is just a corrected version of PIV-NERT, the ideal gas law. Now, what are A and B? Well, you can look up values for A and B for different gases in table 8-3 in your book. And the actual values of A and B are going to vary depending on the gases that you're talking about. So A is the pressure correction, and B is the volume correction. You can find them in those tables. You don't have to memorize them or anything like that. So the pressure correction takes into account attractive interactions between gas molecules that would prevent them from hitting the walls of the container as frequently as they would if it were a so-called ideal gas. So in reality, there are attractive interactions that cause molecules to crash into each other, and that's going to prevent them from hitting the walls of the container as frequently as the ideal gas law predicts. B, the volume correction takes into account the volume actually taken up by the gas molecules. Um, so that is going to be a correction that we do for the volume of the container to make it more like the ideal gas. So A and B are tabulated. They were found by fitting lots of experimental results for different gases. But you can expect some trends. Since B is a volume correction, how do you think B will vary with size of the gas molecule? How will B vary with the size of a gas molecule? Okay, and my program does not like that, the way that I wrote B here. So let's try to correct that. Turned it into a weird little triangle. Okay, well, the bigger the gas molecule is, the more volume it's going to take up, right? So we would expect B to increase in size, or the value of B should increase with the size of the gas molecule. So for example, if you have helium gas versus chlorine gas versus carbon tetrachloride, which of these gases is going to have the highest B? You should be able to predict that without looking them up in the table. You can also probably estimate which one is going to have the smallest value for B. Remember, B is the volume correction factor in the van der Waals equation, and it takes into account the volume taken up by the gas molecule. So the bigger the molecule, the higher the B value we're going to have. The biggest of these three molecules by far is going to be carbon tetrachloride. That's going to be the heaviest one, the largest one. It has the most atoms, it has the most bonds, it has the highest molecular weight. So we would expect carbon tetrachloride to have the highest B value of these three. The smallest B is going to belong to the smallest gas, and helium is the smallest gas molecule of these three by far. Now let's think about A. Which of these gases is going to have the highest value for A? And which of them has the smallest value for A? Let's think about what A is for a moment. It takes into account the attractive interactions between gas molecules. So the molecule with the strongest intermolecular forces is going to have the highest value for A because it's going to have the most interactions between particles. So it's probably pretty safe to assume that the largest A is going to belong to carbon tetrachloride because it's the largest of these molecules. It's going to have the strongest interactions. None of these molecules is polar, but if we had a polar molecule, that one would be the one with the highest A. The smallest A would be the smallest gas in this case. We'll go into that in a little bit more detail next semester when we talk about intermolecular forces. So I would just like to end our discussion of real gases by asking one last question. Under what conditions will a real gas behave most ideally? Okay, this will test our intuition about gases a little bit. Well, you want to reduce intermolecular interactions. And the higher the temperature you're going to have, the fewer intermolecular interactions you're going to have. Think about it. High temperature means that the particles are moving faster. If the particles are moving faster, the collisions are going to be minimized. So the intermolecular attractions that necessitated the pressure corrections are going to be minimized. So at higher temperature, a gas is going to behave more ideally because the intermolecular interactions are going to be minimized due to the motion of the gas particles. What else? High volume. The higher the volume you have, the less you have to worry about the volume of the gas particles themselves. And related to that, low pressure, because low pressure means high volume. So for both of these factors, the volume at high volume and low pressure, the volume of the gas particles is easier to ignore. So it's more negligible. So a gas will behave most ideally under conditions of high temperature and high volume and low pressure.